everybody. Today we are going to discuss about an interesting class of systems which we refer to as liquid crystals. So, in the previous lectures we have looked at order which prevails in the liquid state, and for example we have different kind of structures which are present in solution. For example, micelles, reverse micelles, lamellar phases, bilayers, vesicles, inverse vesicles, and we discussed all this interesting array of species which exist in the solution. And we also have looked at the solid state, which is the crystalline state. Now, in between the solid state and the liquid state exists liquid crystal-like state, which is neither completely like liquid, where the orientation of the molecules is quite random, nor that of a solid where it is completely frozen. So, crystal is characterized by a long range orientational order as well as long range translational periodicity. Liquids, isotropic liquids have short range ordering. There are some interaction between the molecules which actually keep them in a ordered state, but by and large the thermal energy fluctuations are also there, which let the molecules rotate and translate in the liquid state. And in between these highly disordered and ordered states exist a state where you neither you do not have the long range translational periodicity like that of crystals, but you also do not have complete lack of order. So, there is order, there is orientational order to a certain extent, and that is where this state is referred to as a mesogenic state, or also referred to a liquid crystalline state. So, today we are going to talk about the properties of this particular state of matter, which we called liquid crystals, from about a covalent as well as a non-covalent perspective. So, if you look at this particular diagram, it essentially talks about the existence of different liquid crystalline states or phases as a function of temperature. So, you see here as a function of temperature, you can see this is the temperature axis, and these are the different phases which are formed, and the liquid crystals to start with can be broadly classified as thermotropic crystals, and then under thermotropic crystals we have the calamitic and the discotic crystals. And when we now go further, the calamitic crystals exist as nematic phase, smectic phase and cholesteric phase, and then these actually, when you further increase the temperature, they eventually convert into a liquid melt where it has got more isotropic nature. That means it exists as isotropic solution, and there is a certain temperature which is called a clearing point, at which the liquid crystalline phase has completely converted into the isotropic liquid like state. And in between this initial configuration, that is the frozen configuration, the solid, to the final clearing point, there exists a state which is the anisotropic liquid state, where you have some degree of orientational order, and that we can refer to as the liquid crystalline state. And now we will look at some of the interesting examples of these kind of liquid crystals. So, first we will talk about the liquid crystal, that it represents an intermediate state between solids and liquids. And it has been observed that generally the molecules that form liquid crystals, number one, molecular shape is a very important factor, and these kind of molecules which exhibit liquid crystal like behavior are referred to as mesogens or mesogenic substances. So, to start with, the molecular shape is a very important factor, and they can either exist as long cylindrical shape, that is rod like, or they can exist in flat circular dish shape molecules as well. For example, let us look at a couple of examples. So, if we look at compound 1 and 2, you can see that they tend to form long cylindrical like structures. So, these have got long cylindrical like geometry, and in this case you can see this is a phenyl, this is a biphenyl, there is a cyano electron withdrawing group, and there is a electron donating hydrophobic chain. Here in this case of 2, we have got the cholesterol moiety, and then we have got the ester, and we have got the long hydrophobic chain C8H17. So, these refer to the long cylindrical rod like molecules. Similarly, we can have got flat disc like molecules. For example, we can look at this hexa host, where the every hydrogen is replaced with the corresponding ethinyl, phenyl, C8H17 moiety. So, this forms a circular flat disc like molecule, and this is a pure organic compound. In the case of example 4, we can see that it is a copper coordinated complex coordinated with 4 oxygen atoms, which again forms a tightly packed geometry, where you can see the planarity which exists here, and then this tends to form a rod like molecules. So, these are different examples of cylindrical these are examples of the cylindrical and the dish shaped molecules. Now, what are the properties of these molecules? As you can say that when the liquid crystals are formed, there tend to exist intermolecular interactions between the molecules. So, you can have these rod like molecules, and these rod like molecules or the cylindrical like of entities can now arrange in different ways. So, we can have these cylindrical entities which actually stick to each other sideways, or they can stick to each other with some lateral displacement, and they tend to form very different kind of arrangements. And the nature of interactions which hold these cylindrical like entities are very weak interactions. Mostly these are the hydrophobic interactions, and also these cylindrical like entities can actually glide or slide over each other easily with little bit amount of energy. So, that is what gives the liquid crystal its liquid like behavior. And the another computing factor is the thermal energy of the system, is the temperature of the system. If the temperature of the system is very high, then we know that these molecules can actually disengage with the other molecules, because the non-covalent interactions are very weak. They can break these non-covalent interactions and then start swimming around in the bulk, because that is the tendency of these liquid like molecules to actually undergo dynamic disorder like motion in the liquid state. So, so temperature is very important. So, if you increase the temperature of the system, then these intermolecular interactions slowly break and weakens the system, and it first goes more into the liquid state, forms an anisotropic liquid state, and finally, when the thermal energy of the system is high, then the intermolecular interactions are between the molecules practically do not exist. Then the molecules are free to move around in the bulk medium, they form an isotropic liquid melt. So, it is important to keep in mind the nature of these liquid crystals. The second thing is that it is to be kept in mind that, so the first thing we talked about is, the anisotropic shape of these mesogens. Number 2 is dust particles and surface homogeneities can affect the orientation of these molecules. Can affect the orientation of these molecules. and they are actually visualized using a polarizing microscope, where when you pass the plane polarized light which goes to the liquid crystal specimen, and because you have the liquid crystal arrangement in different orientations, when you pass plane polarized light, you will be able to see suitably bright and dark regions having suitable extinctions depending upon whatever light goes to the analyzer. So we can analyze these liquid crystal like states using a polarizing microscope. Fourth thing is that, as I told you, the domains get deformed very easily, and hence formation of liquid crystals is sensitive to temperature. Fifth, the formation of these liquid crystals, it normally occurs above the melting point of the substance, but still the temperature should be low enough such that the molecular motion is pretty restricted and the energies of the intermolecular interactions are strong compared to the thermal energies. So the liquid crystal formation is characterized by reduced molecular motion, so that there exists an orientational order, there exists an overall orientational order long range within the molecules. There exists an orientational order long range between the molecules, and the intermolecular interactions are greater or stronger than the thermal energies. This is important. So, and if, when you will increase the temperature, then it leads to more rapid motion of one molecule with respect to its neighbors, and eventually leads to the formation of the isotropic liquid. So, we now also see now that the different phases that exist are as follows. So, let us look at the pneumatic phase. So, to start with, let us take this rod like molecule. So, this state we can see is the solid state, this is the liquid state, and this is the liquid crystal state. So, in the case of solid, as I told you, these have got both long range orientational ordering. So, you see that they are very nicely ordered, they have long range orientational and translational order. Liquid light state, there is no order as such, Whereas in the liquid crystal state, you will see that now you see that there is a change in the orientation of the molecules. They have adopted slightly distorted or disordered orientations, but overall if you see along a particular direction, there exists long range orientational order, but the long range translational order is missing. And it is with respect to this particular direction that we call as the direction along which the molecules are ordered, that these mesogens are all ordered along the same direction, is the direction along which the slippage of molecules can take place along the rod like axis, and this is what gives nematic phase its high degree of fluidity. So, the high degree of fluidity exists in the nematic phase. And this is also the least ordered of all calamitic phases and is the last to occur before isotropic melting. Then comparing to the smectic phases, we have got these represent a high degree of order. So, let us go back and see. So, here you can see these were the nematic phases, where you can see the cylindrical like arrangement of the molecules along a particular direction. But in the case of smectic, you will see that they first form these first form these tubes along one direction, and then they stack along the another direction. So, this gives rise to a 2D structure in the case of the smectic phases. So, there is a high degree of order in the case of smectic phases, and these are 2D layer arrangements. These are 2D layer arrangements. Again, the interactions exist between the layers and the molecules can easily slip past each other. So, this is what is interesting, and slippage exists between the molecules. Now, overall what has been observed is that these smectic phases are actually obtained by slight changes in the orientation of the molecules which pack the liquid crystal state, and it has been observed that 12 different phases exist. So, just like in solids we have got different phases, in the liquid crystal state also we can have different liquid crystalline phases, and these have been observed to be labeled as SA to SL, A, B, C, D, E, F, G, H, I, J, K, L, and the most ordered state has the highest viscosity for the most ordered structure. So, for example, let us take this particular compound C8H17. So, this compound undergoes 3 phase transitions. You can see as the length increases, it tends to develop some curvature. So, we start say from A, it melts at 24 degree centigrade, with an enthalpy change of 25.5 kilojoule per mole to give rise to the smectic A phase, and then at 39 degree centigrade it converts to the nematic phase. The enthalpy change is extremely small, 0.13 kilojoule per mole, and then finally it converts to the liquid state by decomposition. So, it decomposes to isotropic melt at 42.6 degree centigrade. The enthalpy change is 0.976 is 0.976 kilojoule per mole. So, these are very sensitive subtle phase transitions which takes place when one phase converts into the other, and the energy change associated with this process is also small, and the overall the temperature range over which these phases exist is also very narrow. Then we can now see the next classification, which is referred to as the cholesteric kind of crystals. So, here you can see you have this cylindrical rod shaped molecule, and now the next molecule is below this, but slightly tilted orientation. Then the next one is slightly tilted orientation, then the next one is slightly tilted orientation. Like this, the consecutive molecules which are stacking along a particular direction have got slightly tilted orientation, and you can see that eventually when you go to the this last molecule here, you can only see the top face of the molecule. It has got a perpendicular orientation compared to the first molecule from where the stacking started. So, this arrangement is referred to as a cholesteric arrangement forming the liquid crystal state, and it is essentially characterized in the cholesteric state. It is a helical nematic phase with a helical pitch, and the pitch is 200 to 2000 nanometer in length. So, we see that they change their orientation with respect to one another, and they essentially form a chiral arrangement. So, these are chiral / optically active arrangements. This arrangement leads to the optically active state. And why this cholesteric state is very interesting is because the phenomenon of liquid crystal was first observed in 1888 by Friedrich Reinitzer, who was actually a botanist in acetate and benzoate derivatives of cholesterol, and so these were named as cholesteric phases. Another very interesting property of this cholesteric phase is that they when you increase the concentration, then they tend to assemble further with themselves and form interesting phases which we refer to as the blue phase before they convert into the isotropic melt. So, for example, let us take cholesterol nonanoate. In the case of cholesterol nonanoate, we have the solid at the melting point of 78.6 degree, it converts into a cholesteric phase. At 91 degree centigrade, it forms this blue phase 1. It is in equilibrium, the enthalpy change is 0.07. Then it forms, this is kilojoule per mole, then it goes at 91.3, a very slight change to the blue phase 2, and finally at 91.45 degrees centigrade it converts into the isotropic melt. So these are the cholesteric like phases, and here the enthalpy change is 0.53 kilojoule per mole, whereas here it is 0.017 kilojoule per mole for the blue phase 1 and blue phase 2. Then we can go to the discotic phases, and in the case of the discotic phases what we have is a disc like molecule which can actually stack, and the next stacking can also happen in this way. So this is the discotic columnar arrangements, and I showed you an example. So these molecules are circular shaped or flat disc like molecule, and therefore they can stack along one direction, primarily held by van der Waals interactions, Piper stacking interactions between the functional groups which are responsible for this stacking. And when you have this stacking along a particular direction, these eventually are very interesting because they can lead to charge transfer. So you can transfer of electrons. When you apply a potential from one direction and you have a stack, you can have now the electronic conduction. The electrons can flow along this particular path because you have given it the necessary direction, and therefore charge transfer can take place. And this is of relevance in OLEDs, molecular switches and wires. So we essentially consist of this periodic arrangement of the stacks one on top of each other, and then the stacks can further translate to form these kind of 2D layer like structures which correspond to the discotic phase. And in the case of, so we have looked at the discotic phase, and now coming to the lyotropic phase. In the case of lyotropic liquid crystal phase, these are made up of amphiphiles plus solvent. The solvent can be water, or then these can be some organic solvent, and therefore we know that in order to form these kind of lyotropic phases, for example here you can see this is the lyotropic arrangement. This resembles something called a micelle, and therefore there is a certain CMC which we call the critical micellar concentration to form these lyotropic phases, and as you increase the temperature they eventually melt to give you the isotropic solution. So the lyotropic phase are characterized by this formation of micelles about which we have explored, and this also is a case of a liquid crystal state. So with this background in mind, we can now go and look at some interesting examples of supramolecular liquid crystals which are actually held by non-covalent interactions, and again here there are some prerequisites which are of interest to design these kind of liquid crystalline materials. As I told you, this must be thin or flat like molecules, and length must be at least 13 angstrom, and to have that it will be nice if you can have alkyl chains which are present. Branching must not take place, branching is not allowed, and what you need is anisotropic polarization, so that along one particular direction in which you have the formation of these stacking of these molecules, the formation of the hydrogen bonded chains forming these supramolecular liquid like crystal molecules, you will have more polarization in one direction compared to the other directions. So we can take examples of these. For example, we can take for example, we can have R Rx is equal to Cn, Rx is equal to N. Okay, then we can have the hydrogen bonded this is the hydrogen bonded dimer. So we can have these kind of molecules. So first of all, we can have this highly anisotropic rigid shape, okay, which can give rise to the formation of LCMs, which we call as the liquid crystal materials. And we can also now have these kind of hydrogen bonded dimers, which can form these long chains. Then we can also modify it further. We can have polar groups to enhance the non-covalent interactions. For example, we can have the bis-methoxy substituent. So we have this oxy-azoxybenzene, and instead of methoxy we can also have cyano acid and ester moieties as well. And we can also have other cases where we can have hydrogen bond, further extensive hydrogen bonding. So we have the carboxylic side, and now we have the nitrogen side, and we can have this hydrogen bond which forms a mesogen. This is a mesogen, and a strong hydrogen bonding which forms a stable rigid arrangement, and it leads to the formation of nematic phases. The melting point is 214 degrees centigrade. Okay, so we have a representation of a supramolecular liquid crystal system, and we can also have other examples as well, where we can have cases where we can actually put side chains that will lower the melting point of these systems. So overall, we have seen that there are many interesting examples, okay, and we can also, for example, in the end consider halogen bonded system. For example, we can consider pentafluoroiodo compound. This forms a strong halogen bond with C8H17. So neither of the starting materials A or B are mesogens, but the combination, that is a halogen bonded adduct, gives the smectic A phase which is formed on cooling the melt at 84 degrees centigrade. So, overall I hope I have been able to convince you that liquid crystal entities are very interesting. We have both covalent as well as non-covalent entities which can form liquid crystals and exhibit liquid crystalline state. So, that brings us to a close of the discussion on liquid crystals. We will now look at another fascinating class of systems which are called supramolecular gels in the next lecture. Thank you.